stormwater control measures have, or green stormwater infrastructure has. Um, and many of them, unfortunately, are poorly quantified. Okay, they're poorly quantified. And the way that you can take advantage of additional stormwater control measures is to better quantify them. And I think I need to let my man do a little fix. Thank you. The good news is I haven't moved a slide yet, so it worked out great. Thank you. Well, carbon sequestration is probably of the co-benefits associated with stormwater control measures. Carbon sequestration is probably the one that has the best ability to be measured. It's still not as good as measuring hydrologic benefits or water quality improvement, but at least there's something, all right? And I will share that with you over the course. I'm actually going to skip some of these slides, all right? And I talked about this, that President Obama um, passed an executive order that required stormwater management and carbon to be linked, all right? So this is one of my former students, Dr. Tricia Moore. She's, I think, associate professor now. She's either full or associate professor. She's full now? Thanks for knowing. At Kansas State. And one of the great, and I know Professor O's would say the same thing, one of the great joys of being a professor is seeing your students succeed. It's just the best. It's like watching your kids succeed, right? Your children. It's just the best. And she's done very well. So this was her research. Now, what we did is we looked at wetlands specifically, wetlands and wet ponds initially, to determine if they were sequestering carbon, and if so, at what rate. All right, so we collected a bunch of ponds and wetlands across North Carolina. All right, you see we had a total of 20 ponds and 20 wetlands, and it was and we looked at the different zones. I just spent all this time talking about wetland zones. So there's deeper pools, there's the shallow water zone where nitrogen's being removed, and then there's the temporary inundation zone, which is what gets wet when it rains and then dries out in between storms. And so we wanted to see if the different zones in a wetland would have different carbon sequestration rates. And we did the same thing for ponds as well. We did the deep pond, the shallow part of the pond, and the aquatic shelf of the pond. So she went in, this was relatively hard work, collected a bunch of bulk density samples. We got carbon content, and we were able to collect samples from young wetlands to relatively old wetlands. I think the oldest wetland we have is about 15 years, all right? And the oldest pond we have is about 20 years. And we wanted to see if you substitute space for time, if you could calculate an accumulation rate for all of for these ponds and wetlands, all right? And what you found was that there was carbon accumulating, and it tended to be accumulating in the temporary inundation zone in ponds and wetlands, as well as in the shallow water zone of wetlands. So carbon was in fact accumulating, and we actually could even start guessing or calculating carbon accumulation rates. All right, so here you go. You see the wetland has a much higher accumulation rate than the pond does. The pond has no rate, in fact, at all. It was not a significant change. But the wetlands, at least, were accumulating carbon. Now, should that make sense to us? How do you lock carbon in from the atmosphere into your soil, right? It's done by, God bless you, naturally occurring systems. It's done by plants. Plants are what? And so which system has more plants, wetlands or ponds? We know the answer. And it reflects itself in this graph, okay? So that wetlands are able to sequester carbon at a pretty legitimate rate, certainly compared to wet ponds they do, all right? Now, one of the more fascinating things is if you isolated ponds that had littoral shelves, okay, and you looked at the pond, you looked at the littoral shelf of ponds versus other parts of ponds that didn't have littoral shelves, what do you see? That the littoral shelf, which is, what is that? It's a wetland zone along the fringe of the pond, right? It accumulated carbon too. Does that make sense? In fact, I don't know if you observed what the accumulation rate was, 81.3 for the littoral shelf portion of a pond, and it was 84.4, basically the same accumulation rate, which should make sense because we're in the exact same climate. The ponds and the wetlands were being taken from the same climate. They have the same accumulation rate, all right? The ponds with the wetland portion of the ponds had the same accumulation rate as the wetlands had in North Carolina, all right? So we're like, I got it, I got it, I got it, I got it. Okay. And so you have these different accumulation rates. They had been calculated for different places across North Carolina and North America. And you can start taking these values and start plugging them into a predictive model. Now, I'm going to very quickly go through this, but we also did some work in Singapore with the Singapore National Parks to look at their carbon accumulation rate. And we also did some work in northern and southern Sweden to look at their accumulation rates. All right. Without getting too much into the details, you'll see that the American rates were actually the lowest of the four places we examined. And that surprised me a little bit. I thought we actually would have higher accumulation rates than the Singaporeans because the hotter it is, the lower your accumulation rate is. Basically, the warmer it is, the harder it is to lock carbon into soil. All right. But how much does it rain a year in Singapore? About, I think, 2,000 millimeters a year. It's wet, which means, would you consider that to be a highly productive rainfall? Like, is that a climate that would be highly productive for vegetation? The answer is absolutely. So basically what you see in Singapore is so many plants are able to grow at such a great density that it overcomes the fact that it's warm all year round and the carbon breakdown associated with it. The best one that we found actually was in Sweden, which is in line with what we found in northern United States. Okay. So hopefully everyone's picking up on this, that wherever we were, we found carbon accumulation. We found that wetlands did better typically than ponds, but the inundation zones of ponds or the aquatic shelves of ponds, which look like wetlands, also had carbon accumulation. Well, what about highway corridors? This is a classic rural North Carolina interstate corridor. The interstates, for those of you who aren't familiar, they're the United States' best roads. They're the fast-moving roads. In Germany, you'd call them the Autobahn. I know we have some folks that have been to Germany. There you go, the Autobahn. We call them interstates because they move between states. They move people between and among the 50 states, except for Hawaii. You can't drive to Hawaii. But what we found is, obviously there's a lots of highway corridors, but we had filter strips here, and you have swales here, right? And we're going to talk about swales tomorrow, but some of the swales were wet. So we had standard swales and we had wetland swales, all right? And so what we wanted to look at was, did these parts of the development and the stormwater treatment system, did they sequester carbon? And for example, for vegetated swales, standard swales, the answer is yes, that they sequestered carbon, but the rate of accumulation was much lower, all right, than compared to wetlands. In fact, when you compared wetland swales and dry swales, you can see the total amount of carbon sequestered in a wetland swale was twice that on average of the dry swale. So hopefully all this stuff is making sense, all right? Vegetation drives temporary locking of carbon in the soil. The wetter your system is, the more, and as long as it's not too wet, right? The soggier, or the more waterlogged your system is, the more carbon you're going to be able to sequester and store. All right, versus being ponded. But if you have vegetation, you're going to be able to sequester carbon. Wetlands are better than other practices or other. So anyway, this is my pal. You might recognize Fernando over here. Here we are at a bull ring in Spain. There we are getting ready to dance in Rio. We have to get a good picture of us somewhere in India, right? We need to get Fernando a hat, and I'll wear my hats. He can wear his. Why don't you just wear one of my hats? We'll have a picture made with one of our hats. And so this is the model. Usually he's not in here for me to tease, but this is the model that Sean led the development of, where he took data that we had collected at NC State, and then they harvested a bunch of data from US EPA. Okay? What's that? And US Forestry. Yeah, and yeah. Yeah, thank you. You know your number, right? And so basically, what this model is about is calculating carbon footprints of landscapes, okay? That's wholly different from calculating carbon footprints of buildings. We're only looking at landscapes, everything outside of landscapes, all right? And stormwater control measures are also landscapes, right? A bioretention cell, a constructed wetland, those are landscapes as well. And conveyance systems, standard swales, concrete swales, reinforced concrete, all of those things have carbon footprints, all right? So grass swales have the ability to sequester carbon, concrete doesn't, but they all have carbon footprints, okay? And so essentially the way it works is you've got four things associated with the carbon calculation. One, that when you are using media, all right, to put into a bioretention cell, the media has to be mined from somewhere or dug from somewhere. Well, guess what? There's an embodied carbon associated with harvesting that media. If you bring in rock, that rock has a carbon footprint associated with it. It was probably blasted by dynamite, okay? So the riprap or crushed, so all of that has a carbon footprint. The second thing is when you build a stormwater control measure, it's not like it happens automatically. People have dump trucks, bulldozers, excavators. They have to be run. They're powered by gas or diesel, all right? So there's a carbon footprint associated with building. So the materials that come have embodied carbon footprints. And then there's the practice has gotten built. Then you got to maintain it. Well, does the maintenance happen without a carbon footprint? Nope, it doesn't. In the United States, we typically drive there. All right, well, there's a carbon footprint associated with driving to run the maintenance. And then you're going to mow it. And most of our mowers are gas powered. All right, so there's a carbon footprint with that. So embodied carbon materials, construction maintenance, all of those make your carbon equation get worse. But there's one thing that can offset that. And it's what I just shared with you specifically about wetlands. And it's the plants associated with our stormwater control measure ecosystems. All right? So carbon is sequestered by vegetation inside the SCM. Okay? Or if it's a lawn or it's a wood patch, carbon is being sequestered. Okay? So that's the equation. And then the question is how do you calculate each piece of this equation? Well, we went in, the student went in that Sean hired, and with Sean, and they collected studies that were available in Europe, the United States, both from the government as well as research universities, okay, to calculate embedded carbon and materials costs, to calculate the construction and maintenance costs associated with the types of vehicles that were being used to perform the operation. And then the sequestration part, that was done by collecting studies done on representative uh, land uses associated with each of these stormwater control measures, okay? So, having said all of that, this is what a typical stormwater control measure framework of carbon no, not footprint, because I haven't included sequestration yet, but as far as embodied carbon and construction carbon, here are the practices ranging from best to worst. The best one is the constructed stormwater wetland, followed by the wet pond. Why is that? They're big. You guys are familiar with economies of scale, okay? Bigger will tend to be better, especially if you're not bringing in a bunch of filter media and all that, all right? Wetlands and wet ponds, you're bringing a concrete box and some rocks, but most of it's just digging. On the other extreme, you have rainwater harvesting. Well, what's rainwater harvesting? Typically, they're big extruded plastic tanks or metal tanks that get delivered to the site. So, like rainwater harvesting has a pretty big carbon footprint. Now, you might be able to mitigate that to some extent with how you use the water, all right? But long story short, rainwater harvesting systems tend to have pretty substantial carbon footprints. All right. Doesn't mean they're bad, but you're not going to use them as part of a big carbon reduction strategy. So you might use that rainwater harvesting to reduce the water you buy, all right? So this model factors all this stuff in, all right? And you can see the various landscape types that you can use, all right? And once you log in, you get to pick the landscape type. It could be a pavement area. It could be a wetland or wet pond, all right? It could be a green roof, all right? You can see it right there. And then once you decide what type of landscape area you want, you then have to, as a designer, start putting in values, all right? And this is what makes this particular model a far more precise calculator than most of what's available. I actually say everything that I'm aware of that's available out there, where they use a couple of rules of thumb and they use that to calculate, all right? What this model does is it takes a look at exactly how you have chosen to design this stormwater control measure, all right? And has you input those data because, for example, the amount of gravel you use does matter, all right? The number of plants you expect to grow do matter, okay? It's not just one quick number and we're done. That all those things have a significant impact. How you expect to maintain your practices does matter. And all of that ties in to what the carbon footprint is of that particular practice, okay? How far you have to go to maintain, for example, does matter. If you're going to travel round trip of 2 kilometers, or if you're traveling a round trip of 20 kilometers every time you maintain it, all of that will add up. Okay. And so after these data have been inputted, all right, it looks at the amount of carbon associated with that practice, its construction and maintenance, and it shows how much carbon's emitted associated with that practice, construction and maintenance, and then it looks at how much carbon sequestered, and you subtract the green from the red or the orange, and you get the carbon footprint. Okay, that's how it's done. Now, I'm going to go through an example for time's sake. I think this works out well rather than actually running the model. We have the model here, but rather than running the model. And we're going to talk about dry ponds. Here's the dry pond. Remember, the dry pond is a what? One-trick pony. Okay? It doesn't do a whole lot. It's grassed. We've established that a grass covering is not going to do as much for carbon sequestration as wetland plants. So guess what you can do to a dry pond? You can convert it. You can convert it into a constructed wetland, and you can do so very easily. You basically take that low flow orifice at the bottom, and you put an elbow on the back of it. You raise the water up an average of 20 centimeters, or maybe the maximum height of 20 centimeters. You flood the bottom of your dry pond with 10 centimeters of water, 20 centimeters of water, 2 centimeters of water, and then you put plants in. That's literally all you have to do. And so you've taken a dry pond and you've turned it into a wetland. So therefore, we've taken a dry pond and we've turned it into the best possible practice for carbon sequestration. Okay? So I can take that information about how to have the best possible practice for carbon sequestration. I can like put in the surface area of what we're doing. We're not digging anything, right? So I don't need to worry about that. We are adjusting the outlet structure, so I put some data in there. And I talk about the change in maintenance. But there's not much else to do. It's pretty cheap. Plug in the maintenance guidelines, plug in the sequestration guidelines, and now you can see what converting a dry pond to a wetland will do. This is how much carbon you have to input to make that conversion, including the extra maintenance. All right, there's a maintenance difference, the extra maintenance, and this is the carbon that gets sequestered. Subtract that from this, and you've got a very rich carbon footprint that is well south of zero. And how many, by show of hands here, think that's a good thing? You got it. That's not a trick question. That's a good thing. And guess what else it's doing? It's removing nitrogen better too, right? It's removing nitrogen better as well. So this is one of those things where a simple retrofit can get you better carbon removal as well as better nitrogen removal. And in fact, over the course of a 20-year period, that converted dry pond will get you an extra 23,000 kilograms of carbon, which is equivalent, according to the United States EPA, of 5 vehicles in America being taken off the road. Remember, Americans like to drive, so that's not inconsequential. 5 vehicles taken off the road for a year. Do you have any questions? I do have good news. Senor Fernando is going to be with us today. So if you have questions about his model, you can certainly ask them. He did ask me to give the presentation. Did I do okay for you today, Sean? He's busy. And I also did promise to try to get us done at about 1 o'clock. It's about 1 o'clock. We did start later because we didn't all arrive on time. So I feel like I'm still okay time-wise. Do you have any questions? Okay. What I'd like to do, and by the way, thank you everyone for your attention today. What I would like to do is turn this over to Team Roorkee to talk about what this afternoon's going to be like, where we want to meet, and when we want to meet. So I'm going to sit down and turn the program over to Vinarasi's not here, but do you guys know what's? Oh, there you are. So Vinarasi, please do me a favor, coming up, and let's let everyone know how this afternoon is going to progress. Afternoon and evening, for that matter.